All right, so we're taking a deep dive into this 2023 research article all about compound flooding events,
Okay.
specifically how rainfall and runoff,
Hmm.
can really have a huge impact on coastal areas during a storm.
Yeah.
This paper,
Right.
it's called Development and Validation of Accumulation Term, Distributed and Vaudour Point Source in a Finite Element Hydrodynamic Model.
Mm-hmm.
It really digs into, all the little details.
Yeah.
And I got to say,
It really does.
some of the findings were pretty eye-opening.
Yeah, I thought it was interesting how they, the authors,
Right.
Kendra Dresbakc, Christine Spilka, Randall Kolar, Said Mogimi, and Edward Myers, they didn't just kind of tweak things around the edges of the existing models. They really fundamentally changed how we're
Yeah.
thinking about integrating rainfall and runoff into these hydrodynamic models like
Yeah.
ADCIRC.
Yeah, and that's a big deal because traditionally these models have kind of treated things like storm surge and riverine flooding
Right.
as separate issues.
Right.
But in reality, it's all intertwined,
Yeah.
especially in those complex coastal transition zones.
And that's where those models often fall short. And that leads to underestimations of flood risk. They
Wow.
either completely ignore the localized effects of runoff, or they try to lump everything into these major upstream river flows.
Right.
And this new approach really tackles that head on.
I remember watching Hurricane Harvey unfold and just being in disbelief as those floodwaters kept rising in Houston.
Yeah,
It's such a stark reminder of just how devastating these compound flooding events can be.
absolutely.
This research is so important. We need better tools to accurately assess and predict these scenarios.
You think about the implications for FEMA flood maps and the National Weather Service.
Oh, yeah.
If their models are missing key pieces of the puzzle, the flood risk assessments that they're producing could be dangerously inaccurate.
Okay, so let's get into the nitty-gritty here.
Okay.
The authors introduce a pretty innovative methodology. Can you walk us through it?
Sure. So they're essentially adding a new source sink term directly into the governing equations of the ADCIRC hydrodynamic model.
Okay.
This term allows for the incorporation of both distributed rainfall data and point source data representing localized runoff.
So it's not just about accounting for, how much rain falls over a certain area, but how that rainfall actually interacts with the existing water systems.
Exactly. And that's where the use of the National Water Model, NWM, comes in. It provides streamflow data for, get this, 2.7 million locations across the U.S.
2.7 million. That seems like an overwhelming amount of data to process.
It is, which is why they developed a method for selecting the relevant NWM features for their study area,
Okay.
essentially making sure to only use streamflow data for features that end within the model's wet domain and avoiding any double counting.
So it's a very sophisticated way to harness the power of big data without getting bogged down.
Right.
Now, what about the precipitation data?
Well,
How is that being integrated?
they have several options there. Quantitative precipitation estimates and forecasts, QPE, QEPF,
Okay.
multi-rater, multi-sensor MRMS data, and even outputs from hydrologic models.
Okay.
The key point is that the precipitation data is only applied over areas already defined as wet within the model.
So you're not simulating rainfall over a parking lot, for example.
Precisely. It has to be a surface that's already part of the hydrodynamic system
Okay.
that ensures that the model accurately reflects how rainfall contributes to existing water bodies and influences overall water levels.
Okay, so they built this new methodology, but how do they know it actually works?
Well, they conducted a rigorous validation process, starting with idealized test cases.
Okay.
This allowed them to verify the accuracy of the model in simulating both rainfall accumulation and the effects of localized runoff in controlled scenarios.
So think of it like testing a new car in a wind tunnel before taking it out on the open road.
Right.
You want to make sure all the basic mechanics are sound before introducing all those real-world variables.
And once they had confidence in the model's performance in those idealized settings, they moved on to a real-world case study.
Okay.
Hurricane Irene.
Hurricane Irene. That was back in 2011.
Exactly.
Caused significant flooding along the East Coast.
It made landfall near Cape Lookout, North Carolina, and it presented a unique opportunity to put this new methodology to the test.
Why Hurricane Irene specifically?
Well, they had access to a wealth of validated meteorological data, water level measurements from USGS gauges rainfall measurements, and even streamflow data from the NWM for the region.
Wow, so they hit the jackpot in terms of data availability.
Plus, the area had been previously studied, so there was a solid baseline for comparison.
So it's like the perfect storm.
Indeed. Their focus was on the Tar News Pamlico Sound region in North Carolina.
Okay.
They acknowledged that the existing model they used for this region had a coarser resolution, particularly in the upstream channels,
Okay.
which might affect the perfect alignment between the model and real-world observations.
Sure, but using an existing model was probably a practical choice.
Absolutely.
Allowed them to focus on the integration of the new methodology.
It was a strategic decision that allowed them to build upon prior research and demonstrate the value of their new approach within a real-world context.
So what did they learn from applying this new methodology to Hurricane Irene?
Well, first, they tackled the question of precipitation input time intervals.
Okay.
See, using shorter intervals like 5 minutes would theoretically give you a more accurate representation of rainfall patterns,
Right.
but it also means a much larger data load and more computational demands.
So it's a trade-off between accuracy and efficiency.
They found that using 15-minute intervals provided a good balance, capturing the critical fluctuations in rainfall during the storm without overloading the model.
Okay, interesting. So what happened when they added the streamflow data using their new methodology?
It caused significant flooding along the Tar River, much more so than the traditional approach of using a river flux boundary condition, highlighted just how important those smaller tributaries and their localized runoff contributions can be.
So it wasn't just about the big rivers.
Yeah.
Those smaller streams
Right.
played a big role in those flood dynamics.
Precisely. And remember how they incorporated precipitation data only over wet areas?
Yes.
Well, that also contributed significantly to water level increases,
Okay.
particularly in the Neuse River.
So both of those new source terms, the rainfall and the localized runoff,
Yes.
really essential in creating a more realistic simulation of Hurricane Irene's impact.
Absolutely. And they had the data to prove it.
This is fascinating.
Yeah.
Let's stop here for a moment and we'll come back and continue our deep dive. Okay, so we left off talking about how the model actually performed when they plugged in real-world data from Hurricane Irene.
Right.
What were some of the key findings in terms of validating this new methodology?
Well, the results were very encouraging.
Okay.
Their model, with both rainfall and localized runoff incorporated, it lined up incredibly well with the data from USGS gauges, especially when compared to the older models that didn't account for these factors.
So they had real-world measurements to confirm that their model was on the right track.
Exactly.
Not just theoretical projections.
They saw similar improvements when they looked at the data from the Moss tidal stations.
Okay.
Including precipitation data made a significant difference in the model's accuracy.
It really underscores the importance of those seemingly small additions to the model.
Right.
Who would have thought that capturing those smaller tributaries and localized rainfall would have such a profound impact on the overall accuracy of the flood predictions?
It's a testament to the interconnectedness of these coastal systems.
Yeah.
And their high watermark analysis further validated their findings.
Okay.
This analysis focused on the peak water levels reached during the storm.
Right.
And the model with the added source terms was much more accurate in predicting those high watermarks.
So they weren't just looking at water levels at specific points in time.
Right.
They were also capturing those critical moments of peak flooding,
That's exactly.
which is essential in understanding the true extent and impact of a storm like Hurricane Irene.
Absolutely. But as with any scientific research, there's always room for improvement and further exploration.
Of course, even with these positive results, I imagine there are still some limitations or areas where the model could be refined.
One area they highlighted is the need for more efficient data integration methods.
Okay.
They pointed to frameworks like the NOAA Environmental Modeling System as potential solutions.
Okay.
The goal is to seamlessly integrate data from a wide range of sources,
Right.
weather radars, stream gauges, hydrologic models,
Yeah.
all into a single comprehensive flood prediction system.
That would be a game changer for sure.
It would.
Imagine having a system that can pull in real-time data from all those sources
Right.
and generate highly accurate flood predictions.
It would revolutionize our ability to anticipate and respond to these increasingly frequent and intense flooding events.
What about data resolution?
Yeah.
Didn't they mention that the existing model they used for the Hurricane Irene case study had a coarser resolution,
Yes.
especially in the upstream channels?
They acknowledge that as a potential limitation.
Okay.
And it highlights a critical need for improved inland bathymetry data.
Okay.
You see, while we have relatively good bathymetry data for coastal areas,
Right.
inland rivers and tributaries are often less well mapped.
Bathymetry being the measurement of water depth. Right.
Exactly.
It's crucial for accurate hydrodynamic modeling.
Right.
But the challenge is not just about collecting more data, it's also about making sure that data is readily accessible.
Right.
And compatible with the sophisticated models we use.
It's like having a high-resolution camera but a blurry lens.
Yeah.
You need both to capture a truly sharp image.
And speaking of pushing the boundaries of these models, they also discuss the need for more research into dynamic coupling with hydrologic models like the NWM.
Right.
Can you remind us what dynamic coupling means in this context?
Dynamic coupling in this case means that those upstream connection points in the model would shift as flooding occurs.
Okay.
Allowing the model to adapt to the changing landscape in real time.
So instead of fixed input points for streamflow,
Right.
the model would essentially adjust those points as the floodwaters spread.
Exactly.
Capturing the dynamic nature of these events.
Precisely. It's a complex undertaking, but it has the potential to significantly improve the accuracy of flood predictions.
Especially in those highly unpredictable coastal transition zones.
Exactly.
Okay, so we talked about the need for better data integration,
Right.
improved bathymetry data, and dynamic coupling. What else did the authors highlight in terms of future research directions?
They emphasize the importance of continued research into the calibration and validation of these models.
Okay.
You see, even with these advancements, we need to constantly refine and improve the models.
Right.
To ensure they're accurately reflecting real-world conditions.
This is not a one-and-done situation.
Right.
It's an ongoing process of refinement and validation.
Exactly.
Ensuring that the models are staying ahead of the curve as climate change continues to impact weather patterns and exacerbate flooding risks.
Absolutely. It's about continually striving for greater accuracy and predictive power, recognizing that these models are essential tools in our efforts to mitigate flood risks and protect vulnerable communities.
So we've been talking about this groundbreaking research on modeling compound flooding, and I think it's time we shift gears and discuss the bigger picture.
Absolutely. What's so compelling about this work is that it goes beyond just tweaking a few variables in a model. It challenges us to rethink our entire approach to flood risk assessment and mitigation.
So it's not just about building a better model.
Right.
It's about using that model to inform smarter decisions and ultimately create more resilient communities.
Precisely. Let's take FEMA flood maps, for instance. Traditional maps often treat coastal and riverine flooding as separate hazards, but this research demonstrates that that's simply not how things work in the real world.
Right? Those maps can be misleading, especially in those complex coastal transition zones where the interplay of ocean and inland water is so dynamic.
This new methodology allows us to generate flood maps that account for compound flooding, providing a much more realistic assessment of risk for different areas. Imagine having a map that shows the combined impact of storm surge, riverine, flooding, rainfall, and localized runoff all in one.
That would be a game changer for communities trying to understand their true vulnerability. It would allow them to prioritize infrastructure improvements, target mitigation efforts, and make more informed decisions about land use planning and development.
Exactly. Instead of relying on separate maps and disjointed approaches, we could have a unified system that provides a comprehensive picture of flood risk. This could lead to more strategic investments in flood defenses, better building codes, and even the relocation of critical infrastructure from high-risk areas.
And let's not forget about early warning systems. This research has the potential to significantly enhance our ability to provide timely and accurate flood warnings.
Absolutely. By incorporating rainfall and localized runoff into hydrodynamic models, we can better anticipate the timing and magnitude of flooding. This allows us to issue more precise warnings, potentially saving lives and minimizing damage. It's all about moving from a reactive approach to a proactive one.
It's about anticipating those critical thresholds where compound flooding becomes a serious threat and taking steps to protect lives and property before it's too late.
Precisely. It's about shifting our mindset from simply responding to disasters to actively mitigating risks. This research provides the tools and knowledge we need to make that shift.
So what's the takeaway for our listeners today? What do we hope they'll walk away with after this deep dive?
This research is a call to action for scientists, policymakers, and communities to work together to create a more sustainable and resilient future for our coastal regions. It's a reminder that compound flooding is a complex and growing threat, but it's a threat we can address if we use the right tools and strategies.
We've covered a lot of ground today, from the technical details of the new methodology to the broader implications for flood risk management.
If we connect this to the bigger picture, imagine the potential of applying this methodology to coastal areas worldwide. It could lead to more accurate flood risk assessments, smarter mitigation strategies, and ultimately greater resilience to the impacts of climate change.
It's a powerful reminder that science is an ongoing journey of discovery, and that research like this is crucial in paving the way for a safer and more sustainable future. For our listeners who want to delve deeper into the technical details, I encourage you to check out the original research article by Dresbakc et al. 2023.
It's a fascinating read, and it provides a glimpse into the cutting-edge research that's helping us better understand and prepare for the challenges of a changing world.
That's all the time we have for today's deep dive. Until next time, stay curious and stay informed.